All right, so far we have noticed there are two basic ways to understand rate orders. And number one is to look at the experimental values that are given to you. And doing your math and comparing an experiment with another, you can figure out the orders of reaction. You can also be given a mechanism, and from the mechanism, giving the rate determining step, you can figure out the rate order as well, because the rate order is based on the elementary step of the mechanism, whether it's fast equilibrium or not. There's a third way to figure out the orders, and a third and most important way you can do that, and it's through the graphing of the changes of the concentrations. And it's an integrated equation, meaning we have to use a little bit of calculus here. And the understanding is, the reason why we're using a little bit of calculus here is because we care about how much concentration is remaining over time. So what we're going to do today is investigate our basics and hopefully some of the things you already have in your math class, and then go a little bit beyond to answer some real questions. And we all know very simply that we might have a concentration of A over time, okay, with T, and we have seen it would make sense that the concentration would drop a certain amount, okay, over time. And this is typical, actually, of a first order reaction. Now, the question is, we can see that this change over time isn't linear, okay? And we can see that if I wanted to know something about the change over time, I've got an issue because it's not a linear relationship. So as you guys have probably studied, okay, is that chemistry wants to know about something about this function at different time periods. But more so, this represents your A at some time period only, okay? That's the concentration of A at some time period. What we're after a lot of times as chemists is how much total amount of A has been produced or lost. That's what I'm after, not just exactly at an instantaneous time. So you've been talking about this probably in math class, whereas a slope is a change of y with change of x. Just like I'd like to know the change of y, change of x here, but you can see if I do my slope from a linear point of view, I can see that I have some issues here because it's not going to give me some good data, especially if the function is not linear. So what we try to do is we try to make these 2 points that we're studying smaller. So that's why you learn about limits, hopefully limits to 0. So we have a change of y with change of x. But what I'm going to try to do is try to make those changes smaller. Okay? So as we go forward here, obviously, if we make these changes of y with changes of x so that we get a point, what we call that is a derivative. Now, in real life, we call that a differential. Okay? A differential means essentially what you have is 2 points that are infinitely small, so small they're about a point, okay? So if you think about this, if I make these 2 points so small that they're essentially a point, now what I have is an instantaneous position on that function, and that instantaneous position will tell me exactly, okay, let's say the concentration of A at some time period, okay, exactly what that is. And that's what we like to do is for a rate. It's great to know that the rate is equal to k times, let's say, x to the 1. It's great to know that, but what is it really telling me? It's telling me the rate at the initial concentrations. The initial concentrations of, let's say, A. Let's make that A and keep it simple. And that's great. We know the initial concentration of rate. Well, what good is that for me as a chemist? Because as soon as you add A into the reaction vessel, okay, it's changed, it's gone down, and no longer do I know its rate. So I want some more information. But again, if I use this information, and I have a change of T here, but if I had rate, okay, how fast it goes, okay, what's this rate going to look like? Okay, here's rate over time period. Well, the rate's going to drop as well, because if I start with initial concentration and we're driving the reaction with reactants that are colliding, as it lowers, so does the rate. And all I can know as a chemist from this equation is the initial. I want more information. So I take a derivative, okay? And what a derivative is nothing more than making 2 points small enough to know what that point is at a certain time period. But, okay, great. So I may know the rate at a certain time period, okay? And that's what the derivative tells me. It tells me exactly what the rate is at a certain time period. That's good. But as a chemist, I want more. I want to know what the actual what? Concentration of A is remaining. How much? And that takes something else called an integral. Okay, calculus is based upon essentially 2 points. Okay, they talk about derivatives, which is basically a slope, a point on, let's say, this line that tells me an instantaneous rate at a time period, which is nice, but not great. The next step is an integral. Let me explain. So in any case, just to go through this, we do math. There are proofs that prove things that we know. We know the derivative, okay, of, let's go back a second. Derivative of 2x is x squared. Okay, and this is what? Just the function of it. All right? I'm sorry, the derivative of x squared is 2x. All right? And they're interchangeable, and I'll explain in a second, because in my mind I'm thinking backwards and forwards. We know that. Now, I just showed you the proof, but I'm not going to do there and prove it to you, because essentially I'm going to use these proofs. That's what math does. It takes these big proofs and proves it, and then you get to these rules that you learn, like your trigonometry rules. All right? And there's a couple of ways to write it. This is the differential of x, okay, of this value over what? D of x. So this is the differential of x squared. Now, x squared is not this line. It's another function. But this means take a small piece, or at least a small y, over the small x, and this is what I get. And there are proofs for that. No big deal. I'm not going to get into that. But what does x squared equal 2x mean? So if I have a function x squared, okay, here is that function, as you guys have learned. What does a 2x mean? The 2x means is that as long as I pick a point, well, let's say I pick a point at 2, all right? So if I pick the point on 2 on the x-axis, 2 times 2 means right at this point my slope is 4. If I pick 3, my slope is what? Okay, 4, and you can see what's happening is because this is a exponential curve going up, slope is steadily increasing. That's what it's telling me. But great, cool, but what does that really mean in life? Okay, again, it's nice to have an f of x function, but I'm not stuck on just knowing the rate at a particular time period. I want to know how much A is remaining. It's the next step in calculus. Derivatives just give us a point, what the slope is, what the actual rate of change is at that point. Great, but not enough information for us. So what we're going to do is something called integrations. We want to find the actual area under that function. Okay? For instance, here's a function. I want to find how much of y is building up as I change my flow rate. I'm changing my slope, my rate, over a time period. Okay? This is increasing, this is decreasing. How much of y am I adding over a time period? That's what we want. How much? I want a way to link time, which will be my x-axis, and how much A is remaining. Think about it. H2O2 has a shelf life. H2O2 spontaneously decays into water and oxygen. So when I produce H2O2, it's decaying. It's spontaneous. It does decay. It decays slowly by itself, but it is. All right? How long is the shelf life? My friends in chemistry, if I understand calculus, I can solve for how long it's going to take for it to totally decay. And I can put a shelf life. Isn't that more potent? How long is it going to take for the reaction to run out? Okay? Or what time will it be when the reaction rate becomes this? All of these things are tied to how much of A, not just stuck with what exactly is the rate of the time period. We know the rate at this time period, let's say at 0, but after that it changes. So this is very limited. And even the derivative is very limited because it only tells me a point in time, but it doesn't tell me how much. This tells me the flow rate at a certain time period. I want to know how much flowed, how much was made. So what we do in the next step of your calculus education is do something called an integral. An integral means that you're going to add up all of the differentials. Differentials are those points, the small tiny slices under that curve, and you add them up and you figure out how much. Interesting enough, an integral, okay, is the opposite of a derivative. So if the derivative of x squared is 2x. The integral of 2x is x squared, and I'll explain that. So sometimes they call it the antiderivative. But as you can see, what's happening here, when I had the big what? When I had the big blocks, there's a lot of error. If I made these into smaller differential blocks or little tiny slices limited to 0, I could get an excellent answer of what this area under the curve is, which will tell me how much A has been made at a certain time period. That's what I'm after. Okay, not just a point on the curve. This will tell me what the rate is at that point. The rate is here. Great, nice to know. But how much have we collected or lost or made? That's what I'm after. That's what most people are after. Rate is great, okay? But the integral is even more information. So we're adding up all the little basic slices of those differentials. And we add them up to get a total amount over a time, over a function. So as I said, the derivative of x squared is 2x. The integral is x squared. And it's, now again, I can prove that to you. I'm not going to spend the time with the proof, but let me show you how it works. Okay? Now, we use a S symbol to show the sum of all the differentials of our function. So you're going to see that maybe. And I'm probably the first one to show you that. Okay? Now, think of this as a great analogy. It's not mine, but it's a great analogy. So integration is like filling a tank from a tap. Okay? So you open up the valve. Opening up the valves, you're changing the flow rate, which is a function. As you turn and go faster, more and more water come out. So your derivative or differential represents what the flow rate is at an exact time period as I'm turning my hand faster. As I open the valve, more and more water is flowing out. The differential or the derivative will tell me exactly, okay, what the rate of flow is. But it doesn't tell me how much water I'm collecting. So if you look at how we do this, it's pretty amazing how potent this is. So we have a function. It's 2x. What does this mean? My flow rate is steadily increasing as I open up the valve. Because the water's under pressure, as I keep opening up the valve, more and more water is coming out. And if we were to plot that function, it's a 2x. Now, how much volume am I getting? Well, think about this. When you integrate 2x, you get x squared. X squared tells you how much volume. Even though the flow rate is a steady change, you can see it's an exponential increase in the amount of volume. So this is the derivative. This would be the integral to tell you how much water. All right, so as the flow rate increases, the tank fills up faster and faster. With a flow rate of 2x, okay, the tank fills up at x squared. So they're inherently tied to each other. This is cool information, but this is so much more powerful. Okay? So that's what I'm after. Again, slope of 4, the slope's going to change. Okay? And this is our flow rate. And again, they're inherently tied together. So what I'm after here today is to show you that we're going to take our rate laws, and I am going to make derivatives or differential equations from them, and I am going to show you the equation we get when I integrate that differential equation. And it's going to give me a value that ties in temperature, it ties in time with the changes of concentration. I will now be able to know, because I'm integrating, how much, okay, how much A, okay, over some time period I'm collecting as this function runs its course. I can now say from time initial, okay, to time 0, okay, how much A has changed from my function. That's what the integral does. And I want to know that. As a chemist, great to know exactly what the rate is at a particular time period, but isn't it more powerful to know exactly how much of my reaction A is missing, or in this case, product gained, if you want to look at it that way. In this case, it's A lost. That's what I want. Okay, let me show you. All right? And again, we have a time factor, we have an amount. I am able now to say how much time will it take for us to run out of A? How much time will it take for the reaction's shelf life to go its expiration date? These are all important scenarios. So let's continue with the integration and the calculus. So let's go here, brand new screen. You can just watch. I do have another one of this, and I wanted to show you how powerful this is. Okay. If you have some of the calculus, great. If you don't, just try to follow along, okay? When you're able to start understanding how powerful calculus is, you'll wonder why it took so long to teach you this, all right? And I did all these questions in high school, took calculus and everything else in high school, but it wasn't until I really saw this in college that I truly understood what I was doing in math class, all right? So, let's start with an equation. Let me take this off the board for a second. All right, we're going to start with zero order reactions. Now, this is a weird reaction. Okay, why is it a weird reaction? Because these are far and few between. So we're starting with zero order. What does that look like? That looks like R is equal to K, A to the 0. Okay, and what do we have? Well, because it's R equals K to the 0, it's R equals just K. That means we have a reaction where what? We don't have the initial concentration has no effect on the rate, just the K. They're far and few between, but we do have some of these. For instance, here's what we have. Zero order, or zeroth order. Okay, what do we have? We have A going to products. Keep it that simple. What's my rate law? R equals K, we get experimentally, A to the 0. Okay, what kind of reactions are zero order? Well, I'll tell you this. There's one very, very important one, photosynthesis. Photosynthesis depends upon the light reactions, okay, not necessarily concentrations of what's around it. So what starts photosynthesis is light. You can't really change it with reactions. Okay, so there's an example. Again, far and few between, but I'm going to start with zeroth order. So, what do we have here? R equals K. We got this experimentally. Now, let's write rate law a little different, or the rate. I can talk about rate in terms of the disappearance of A. So let's do that. So I've got negative, okay, change in the concentration of A over the change in the concentration of time. That is equal to my rate, right? The loss of A over time, it's a negative because we're going smaller. I can also evaluate the rate in terms of the gaining of the products. But in this case, I'm using A. Now, I'm going to make this equal to my rate law because this rate and this are the same. So this is equal to K, A to the 0. All right, great. Moving forward. Now, what am I going to do here? Well, I'm going to kind of move some stuff around. Well, what I'm going to do is take a derivative. Take a derivative. So I'm going to have the negative d of A over dt. What did I just do? I took a differential, which means small spot of A. Right now I have the change of A. The change of A could be some large change. Y final minus Y initial. Could be a large gap. But because what? I want an instantaneous point. That means the differential of A approaching to 0, and the differential of T. I'm getting an instantaneous rate. An instantaneous rate. Okay, from my initial condition. I can do that. So if you think about it, all right, if I have a graph, all right, if I have A, I'm looking at the instantaneous rate right there. What's that instantaneous rate and what's that direction? Okay, of course it's going down. So I'm getting an instantaneous rate. I can do that. Still equal to the rate. Now, what's it equal to? Obviously it's still equal to K to the A to the 0. Now this is called a differential equation. Okay, another powerful part of calculus is I can start making equations equal to each other. So I made this differential and I have it here. Okay, let's rearrange a couple of things. Okay, first of all, I want to get rid of this negative sign. So I got negative K. I'm going to bring dt over here. Okay, and A to the 0, well, that's 1. So that doesn't do anything. So what I have is d of A equal negative k dt. All right, now I am going to now integrate. Okay, now integrate is at s. I'm going to take the sum. Now, notice I put the integral sign behind my constant. I can't integrate a constant. I can only integrate things that have been differential. Okay, so I can't integrate just a regular number. It doesn't work. I can integrate the differential. So in any case, what is the derivative of a? If this is the derivative of a, what would be the opposite of a? What was it? It was a. So now when I do an integral, what I'm doing is I am essentially taking if this is a function, let's say this is a function, I'm counting the slices of the change of a over t, and I'm counting the slices from 2 points. 1 point is going to be from a initial, okay, to a final. So this point here where I start would be a initial. And this, where I stop, would be a of some time period, which is a final. So when we do a integral, we're going to talk, it's called a definite integral. We're going to tell us where we're going to take those slices. So we're going to go from a of t, that's the final, minus a to 0, which is the initial. So finus minus initial. And the same thing here. We go from t0 to whatever t becomes. That's all we're doing now. Now we're just telling our math where we're taking these slices of these differentials under the curve from. Okay, so differential of a, that's the what? That's the derivative. The integral is the opposite, so, okay, what would that be? A itself. Okay? So we would get a. Now the thing is, I took slices. So I have a, some time period, or final, a at some time period, which is final, minus a of some initial. That's what this gives me. Okay, I'm taking whatever the value is here, subtracting it from here to get that difference of these slices. That's what this gives me. And I pull this out, the differential goes away. Okay, that was a derivative, that was the opposite derivative. You went from this to a derivative back out. But with the slices of the concentrations from a to t over this function. Okay? Well, there is no function because it's 0, but in any case. Now what do we get? Equals, we still get negative k because that's not in the integral, it's not, hasn't been made a differential derivative, and you would get the same thing. You would get time minus time 0, but since time 0 is going to be 0, it's just time, so it's just kt. And notice the integral of this is just t. Just like the derivative of some number is just d of that number. Or that number. So that, my friends, is the integrated equation. And look what it gives me. I have an initial condition, a final condition at some temperature. There's the link, because I'm adding these things. Now, what's really amazing, I think, is now you can rearrange this one more time. Watch what I do here. Okay? I'm going to take this expression here and put it on the other side. So what I get is a of t, that means a concentration of a at some time period, whatever we want to decide it might be, is equal to negative kt, that's the rate law constant, times some time period, plus the concentration of a initial. So look at that, people. I have a time period, knowing the what? The rate law constant. If I know the initial conditions after some time period, I can solve for exactly how much is left. That's what integrals do for me. You could never do that with just a derivative. Derivative is just a point in time what your rate of flow is. I don't know how much water goes in the tank. How much A am I making or losing? Okay? More importantly, though, by me rearranging this, there's another way to look at it. This is y equals mx plus b. Hey, what do I have now? I have just made a linear equation out of something that's not linear. We love to do this. in science. What's our y-axis? A of t. What's the slope? Negative k. So my slope is negative k. That's my slope. My x, of course, is time period. And my a of 0 is my what? My y-intercept. My friends in chemistry, if you have a zero order reaction, you are going to have a graph plotted with a change in concentration of A over time, and it'll be a negative slope. And the slope is negative K. So, how do you know something is zero order? Well, if you have concentration changes, if you have what the concentration of A is over time period, and you plot it, and you get a negative slope over time, plotting that with time to get a negative slope, you know it's zero order. That's the third way now. We have the experiment, we have the mechanism, rate determining step, and now we can gather the data and plot it. This is first order. If you have a first or second order, it will not plot this way. It'll be a curve. It will not do this. Okay, so that's how we test. Okay, let's do first order now. Now I'm only giving you only first order with one element, okay? So R is equal to K A to the first, okay? And let's go see what kind of graph it does when we integrate the same way. I'm going to go a little faster, but it's the same deal. Okay, so let's go down. And let's go to the next page because I feel like it. So first order. What does that mean? Well, I have A go into some products. R experimentally gives me A to the first. Okay. So let's change R. R can be related to the what? Negative change of A over the change of time. And that's another way to think about R. Equal to what? Well, I forgot. There's a K here. Rate law constant. K A of the first power. Okay, we're going to do the same thing. Let's make a differential out of it. Let's do a derivative. That gives me negative D of A to the first power, or just A because it's just A here, sorry. And then over D of T equals K to the A to the first. This is already different because before the other one just canceled out, but this one does not. Okay, rearrange. Okay, so we get D of A equals negative, the negative on the side, K T, sorry, dt. Just put dt on the other side. Of what? Well, A of to the first power. I want to bring this downward though. I want to bring this A back to the D of A because this is D of T. This is the differential of time. This is the value of A. I want to put that next to my differential of A. So when I solve for it algebraically, what I get is 1 over A to the first power. So that's what I have so far, party people. And what does that mean? Okay, well, I'm now going to integrate. And I'm going to integrate from what? I integrate from A to some time period that we care about, whatever that might be, from the initial, this is our final, that's our initial. And then we have what? We have the other one, which means you're initially at time 0, that's our final. And this is time, whatever it might be. Okay, now, different proof. Anybody know what if this is 1 over A, what is that the derivative of? Right. The 1 over A is the derivative of the natural log of that value. So if the derivative, if this is the derivative, if this is the solution for the derivative to go backwards, we have the natural log of A. Okay, for those that are studying. So to integrate this, we get natural log of A. So what we get is natural log of A. Now, of course, what is it though? Final minus initial. So I get the natural log of A, it's my slices that I'm subtracting, right? From some time period, minus the natural log of A0 equals negative, same problem here, t is 0, so it's just going to be negative kt. I'll be doing the same thing with t, but I don't have to because t0 is just 0, okay? Negative kt. Now rearrange this. I'll get the ln of A of some time period, that's the concentration after some time period, equals negative kt, okay, plus the natural log of A from initial conditions. What does this give me? There's my y, this is my slope, plus b. What graph do I have? If I have a first order reaction. If I have a first order reaction, party people, think with me for a second. My y is going to be the ln, the natural log of A. And my slope is still negative kt. And of course my x is still time. And you might say, well, that looks a lot like the other one. Sure, one difference though. If it's first order, your y-axis is just the concentration of A. If it's zero order, the y-axis is the concentration of A. But if it's first order, it's the natural log of A. All right? So yes, it gives you the same graph, but from different values, and they hold you accountable. If something is first order, okay, to know it's first order, you can graph the changes of A over time period of the reaction, do the natural log of them, and you will get a straight line, okay, if it's first order. If you take your A's and do the natural log, you will get a straight line that's a negative slope. These are the same slopes, but different y's. If it's not first order, you will not get a straight line. It'll be curved, it'll be going up, so forth and so on. So this graph proves to you if something is. If you have no other information, but just changes of your concentration of A over time, and you want to know it's first order, okay, do the ln of those changes over the time period and see if you make a negative curve, and that's how you prove it the final way. Now we have second order. Now second order is R equals K A squared. So let's do that quickly. Who has seen any of this before? Who has seen integrals before? Okay, thank the world. Okay. Now, so Christian, I'm boring you.
No, we do it differently than Mr. Ski does.
Okay. Not Mr. Ski he's doing it from his perspective. I'm doing it from the science perspective. We meet in the middle somewhere. Okay? All right? I don't know where that somewhere is. Okay? But we meet somewhere. Okay, any case. Here we go. So R is equal to what? Okay? R is equal to, let's do second order. It's not to be crazy. Second order reaction. Now, the second order reaction that I'm giving you is specific. Okay, so if we had different second order, like you can have a second order with what? 2 x's or 2 y's for a reaction. We're going to just do it from the perspective of, like I just drew, 2 a's. So we have 2 a's going to a product. But you can have a second order reaction overall with an A and a B, or X and a Y. I'm just giving you this scenario only. If you do it that way, you need another derivation. But we're locked into this. Okay, so what's R equal? R is equal to K. Of course, this is A squared because it's the only elementary step. Change of R. Well, change of rate would be what? A negative change of A, concentration of A, okay, over the change in T. That's my rate. It's equal to K. A squared, my friends in chemistry, this is a differential equation. Let's take the derivative. We get negative D of A, Christmas, over what? D of T. equals k, okay, of a squared. Differential equation. Okay, like before, all I'm telling you is what? This rate is equal to now a point time period, an instantaneous rate. Great, still a rate, but not very powerful. Okay, so what we do is we're going to integrate. Before I do that, I'm going to make some sense of this, rearrange. Okay, so I get d of a. Okay, I'm sorry, not d of a. I get d of a this way equal negative k d of t a squared. I want to put this a with this d of a. I want to put this value of a with the differential of a. It's the only way that would make sense. So when I get rid of it algebraically, what I get is 1 over a squared. Okay, let's differentiate our hearts away. I'm going to go from what? A from some time period, it's my final. A from initial conditions, time, some final time, and t at some initial. Okay, guess I have to work with Christian again. All right, what's the proof? If the proof of, what's the integral of 1 over x squared, gosh darn it?
Negative 1 over the concentration of A.
Okay, so right. So what you get is you get the following. All right, so this is the derivative. We're getting back out what the solution was. So the derivative is 1 over a, so we're getting back out what the antiderivative is. Okay, what we get is, all right, is we get negative 1 over, yeah, concentration of A, and that would be from the T, okay, minus 1 over the concentration of A from initial conditions equals, okay,
Minus and minus.
minus a minus is correct, thank you. Okay, equals, okay, the same thing over here we've been getting is negative k of t for the same reasons. Let's clean this up. I'm almost done. So this becomes a what? Well, many ways to do this, but what you get is, when you clean this up, is positive kt, okay, plus 1 over a of 0 equals 1 over a of t. Now what does this graph give me? It gives me y equals mx plus b, and here's a difference in this graph. Difference is this graph is going to give me a positive slope. I still have my y-intercept. I still have my k as my slope, but this is going to be what? The y is 1 over the concentration of A over t. So, getting back to my graphs here, another way to verify or determine what your values are is you notice that this is now a positive slope. This is 1 over the concentration of A. All right? So, what you're left with, and is what you're responsible for knowing, is that the different orders will give you different graphs. Okay, now, do I have to go through these proofs to show you? But I hope you pick something out that this gives me important information. All right, now, if you look at your reference table gives you these orders, or these functions. Okay, now, we go to your reference table. Let's see, I go here. Let's make this bigger. Here's what they give you. They don't label it. They don't give you 0 order. You're not going to see 0 order, but they give you first and second order. So what they did was they give you this, which is first order, and second order. So the first one is first order, okay? And if you just put this over here like we did, negative kt plus lim of a, you've got the y-axis being a of t. Lim of a, I should say. ln of AT over some time period. And then if you do the second order, you notice the y, this would be your y what? Intercept. Okay, this would be plus 1 over A naught, or A initial, you have 1 over T. Okay, so these are given to you. Now, you can use these in any way you like. Now that you have these given to you, and knowing that these are integrated so you can solve for the what? The amount of slices under the curve, or how much, look how powerful this is. How much time does it take for me to take a reaction that has its own rate law to go from initial condition of, let's say, 0.2 molar to 0.01 molar? I can solve for that time period because now I have a graph where I'm counting, basically the integration is counting how much stuff I need to get from these two positions and how much time would be in my graph. All right? So I'm able to solve for the time it takes to go from a concentration to another. That's powerful. How much time does it take to run the reaction? You don't get that from a derivative. Derivative tells me that what? The actual rate at that second. Well, that second's gone. This tells me how much at a certain time period now. I don't have to say, oh, that rate's gone, this rate's gone. I can solve that. If I know the time I need to run a reaction, I can now solve for how much stuff I better start with to get what I want at the end. It's great that I set up a factory and I'm making shampoo products, but it takes 4 days to make one run. I'm not using my integrated formula. I need to do this in an hour. What do my concentrations have to be? That's how we use it, okay? And that's how we use it. Now, a couple of things you should recognize. If I do rate, concentration of A, we do rate over time. Let's do it this way. If it's zero order, kind of interesting when you look at these graphs, okay? If we do concentration of A, over, let's do rate, the rate of reaction over time. If it's zero order, why is it flat? Because it's independent of what? The concentration. If it's first order, gives us our classic half-life curve. Classic half-life curve. Meaning, if I've got, I don't know, this was 10 grams of the reactant, okay, at a certain time period. Let's make it 10 seconds. All right, that's not 10 seconds there. 10 seconds here. Well, now when I have 20 seconds, I have 5 grams. First order is classic, what? Radioactive decay. All right? And then we have second order. Second order does something like this. Probably doesn't come up, but it does that. We don't often look at those rates. We look at them this way to get the straight lines. Obviously, we get this straight line for zero order. Okay, but what will come up is knowing that this one right here is the classic half-life curve. Okay, and when we talk about half-lives, we'll do that tomorrow. All right, so that gives you the integrated equations, and hopefully you know when to use them.